All right, 7.3. We're going to be working with a special number that we notate with the letter E. It is called Euler's number after the mathematician who discovered it. We also call it the natural base. And when I say special number, I mean it's a special number similar to pi that we've worked with and our imaginary number that we notate with on the letter I. It's similar in nature to those. It's approximately equal to 2.71828, but it's going to, keep going. So this is an irrational number, right? It's neither going to terminate or repeat. It does not terminate or repeat. That's what makes it irrational. Um, it is in in calculus. What the rule says or what the pattern says is that if you have an exponential expression that looks like this, okay, n being the variable there, as n gets closer and closer to positive infinity, so as our value of n goes up in value and gets closer and closer to positive infinity, we call that the limit, and it's written like this in calculus. We say that we know that it gets closer and closer to the value of e, which is this approximate 2.71828 number. All right, so that's where this is coming from, and the whole idea behind it. On your calculator, which we'll need this key eventually, not today, but we will need it eventually. You can find this key above the key that has the L, capital LN on it. And so see if you can find that right now, and eventually we will get to that on the calculator. All right, because this E represents an actual number, it's irrational, but it does represent a number. We can treat the letter E just like we would if it were an actual number. So if we look over on our worksheet on number 1, ooh, sorry about that. You can see that we have e to the negative fifth being multiplied by e to the second. So the base is the same. We've got a base of e. And so we're going to rewrite e, and we'll add the exponents, just like we would for any other exponential expression. We would end up with e to the negative third. We, of course, don't want to leave a negative exponent in our final answer, so we're going to flip it down into the denominator, and this will be the final answer for that. For raising e to the fourth to another power, negative 3, so we've got a power to a power. We're going to follow the same rules we've been following. Multiply the exponents. Again, I end up with a negative exponent. I don't want to leave that in my final answer, so we're going to flip it to the denominator to simplify it. Number 5, raise the numerator to the second power, as well as raising that denominator to the second power. So all these rules we're following are the rules we've been following for our exponents. So that second power, remember we have to raise the coefficient to the second power, so 3 squared is going to give us 9. And then here we have e to the third raised to the second. So that looks like our number 3 up here, a power to a power. So we're going to multiply the 3 and the 2 together to give us e to the sixth. Same thing in the denominator. Don't forget to raise the coefficient to the second power. And then we have e to the second raised to the second. So we're going to multiply them. And this is correct, but we're not done. We can simplify it. So if we simplify our coefficients, we'll end up with 1 in the numerator, which I'm not gonna write, and we'll end up with 4 in the denominator. And then we need to simplify our e exponents, our e exponential expression. So we have e to the sixth divided by e to the fourth. So we're going to subtract e to the sixth minus the fourth. That will remain in the numerator. And since it's positive, a positive 2, then we're going to just leave it there, and this will be our simplified answer. On 7, we have two exponential expressions with coefficients. All right, so that's different than number one up here. Number one, we had coefficients, but they were one, so we didn't have to do anything here. Down here, we have two exponential expressions with coefficients that are not one. So we've got to remember to multiply those coefficients together. 3 times 2 is 6, and then we'll multiply our exponential expressions together. They have the same base. The exponents look different, but they are different, but they're the same term, or they're like terms. So we're going to rewrite the base, add the exponents, and we'll end up with 6e to the 5x power. That's as simple as we can go. We can't do anything else with those variables. Now, when we first look at 8, it looks pretty complicated because we don't have anything alike that we can multiply together. We've got a radical, and then we have an exponential expression. So the most likely thing to do would be to take this radical and factor everything underneath the radical, pull it out, and see if we can get something that we can multiply to this 2e to the negative third. If you look at that, we're looking at the square root of, so we're talking about the square root of 9. Remember, we can split these up. We could say the square root of 9 times the square root of e to the fourth. You don't have to write this out. I'm just pulling it apart to show you. And then here's the part we need to multiply it by. Square root of 9 is 3. The square root of e to the fourth is e squared. Right? If you can envision 4 e's being multiplied together, we're talking about an index of 2. So we want to pull them out in groups of 2. And that would give us 2 e's being recorded outside the radical for our e squared. Now we have terms that we can multiply together. Now it looks very similar to number 7. So we have 3 times 2, our coefficients multiplied together. We have the same base, e. We're going to add our exponents. And that will give us 6e to the negative first power. We don't want to leave the negative exponent in our final answer, so I'm going to leave the 6 in the numerator. The numerator is not being raised to the negative first power, it's just the e. So I'm only going to take that e down into the denominator. Now, number 9, again, looks a little iffy, a little complicated until you just think back on your rules for your exponents and look and see what you have there and just think through it. We are always looking for the same base. If we have two things that are going to be divided or multiplied together, the only time we can do anything with those exponential expressions is if the bases match. Well, they do match here. So just follow the rules, even though it's going to seem a little bit weird because of that binomial exponent. So we're going to rewrite the e. We're going to subtract the bases because we are dividing these exponential expressions. So we're subtracting x plus 3. You need to put that in parentheses because this is a subtraction sign right here, which means it's going to affect the sign on both of these terms. So you don't want to forget that. If you put it into parentheses, then you hopefully will remember to distribute that negative 1 out to both terms there. Okay, and then if we just further reduce that, the 3 minus the 3, positive 3 and the negative 3 will cancel to 0. So we end up with e to the negative x power. And then we're going to take that. That's a negative exponent. Now we don't know what it is because that's where the variable is, but we do know it's going to require us to reciprocate the base that's being taken to it down into the denominator. And then it becomes positive. So even if we don't know what the variable or what the exponent is, because that is our variable, you still need to follow the rules of not leaving a negative exponent in the final answer. All right, so now moving down to 10 and 11, we're going to use our calculator to evaluate these expressions. If you go to your calculator and find the LN button, should be on the left-hand side of your calculator, about halfway down, most likely. If you see that, we need the e to the x button that's above that. So the way to get to that is to hit the second button and then the LN button. All right, and you'll see it should pull up. Most of your calculators are probably going to pull it up with the caret already there, and then possibly even the first, the opening parentheses. Okay, this is where you're going to put your exponent in. So if you hit second ln, this right here should pop up on your screen, and then over like for number 10, all we're going to put in is the 7 and parentheses. All right, then you'll hit your enter key, and hopefully you have achieved this answer right here. 1900, I'm sorry, 1096.633. All right, if you try the same thing on number 11 again, so second ln, now when you put, I'm going to do it right here, I'm going to write it out right here, it should come up with e caret opening parentheses. If it doesn't come up with the opening parentheses, put it in. We need to keep these exponents in parentheses, especially when we're dealing with more complicated ones. Make sure right here, you guys, a lot of you have trouble repeatedly with the calculator giving you error messages because you're using the negative sign right here. I'm sorry, the subtraction sign right here instead of the negative sign. You need to use the negative sign, the specific negative sign. It's typically at the bottom of your calculator on the right-hand side, like the bottom row in parentheses. Okay, that's how you know it's the negative number. It is completely different than the subtraction. And then type in your 3 divided by 2, negative 3 rather, divided by 2, and parentheses. Hit enter again. And then in this time, you should end up with 0.223. We can just round it off right there at the thousandth place. Okay, so now we're going to be learning about the natural base functions. So you can see examples of those at the bottom of the page, 14 through 19, and they are going to take the form over here, y equals a times e raised to the exponent r times x. So we have 5 variables there that we need to recognize and be able to interpret. You've got your normal y and you have your x. Those are just points on the function. So the x here and the y over here. Okay, so that's your normal xy that you see in a function. You have your a right here, which tells us in general, just like it has in all the other functions, kind of whether we have stretch or we have shrink on the graph, whether it's inverted if it's negative. So this a value is going to work very similarly again. The e is your natural base. Okay, so this is Euler's number, the one that is approximately 2.7128 that you can find on your calculator by hitting the second ln key. And then we're going to raise that to the rx, so whatever the x variable is for the point, and then r is our growth factor. Okay, so this is what's going to determine whether we have decay or we have a growth function, which is what they've asked us to identify in 14, 15, and 16 over here. If a is greater than 0 and r is greater than 0, so that I'm talking about a scenario like this right here, you're going to have exponential growth. So we're going to have to be able to identify our r when we get over to these exponential functions. If a is greater than 0, so you'll see in both of these examples, growth and decay, a is going to be greater than 0. So we're not dealing with anything less than in this example right here. But r, if it is, and you can see in yellow here, if r is less than 0, then we're going to have exponential decay. So coming back over here to number 14, if we're going to identify our r value, because that's what's going to tell us whether we have decay or growth, we can see that our r value is this, we go to the exponent right here, and it's the coefficient of our x variable. So in this case, r is 2. All right, since r is greater than 0, that is describing this explanation over here in green, then we know for number 14, we're going to have a growth function. In number 15, we're going to come in, find our exponent, identify what's being multiplied by the variable x, in this case, our r value, it's hard to say, is -5. That describes the situation over here in yellow. R is less than 0, so that means in this particular problem we're going to have a decay function. And then in 16, we can see that our variable, the coefficient on the x is -1. That should not say a, that should say r. And since it's less than 0, then this one will also be a decay function. Now going to the back of the page, we're going to start graphing the functions and stating the domain and range. Before we do that, I want to just show you the parent functions on the natural base function. So, we always have a parent function that's the most basic of that type of function. In this case, the growth parent function looks like this graph in green, and it's always going to have this y equals e to the x power. It's going to have that basic form. The decay is shown in yellow, and it's going to be y equals e to the opposite of x. Okay, so that's how we're going to get that that slope going down left to right. The interesting thing, if you look at the growth function, I want to point this out to you. It's running through 1, 1. I'm sorry, 0, 1. So is the decay function, 0, 1. So, sometimes our parent functions run through the origin. In this case, it's going to run through 0, 1. If it is a growth function, this point up here that I graphed in is 1, 2.718. So this is 1. I really could have written in 1, e. This is Euler's number right here. All right, so that's just something that I wanted to point out to you for you to see that. You don't see that in the decay function, but you do see that in the growth function. Now coming over here to actually graph number 20, just some things to look at. You have an a value of 3, so we know this is not going to be inverted. It's positive. And it's 3, so it's going to show a little bit of stretch here on the graph. Our r value is 1, so we come up to that exponent. That x is being multiplied by 1, so that's greater than 0. So we're expecting growth on this graph. So just to keep that in mind in case something happens and you don't get growth, that you might want to go back and double check your arithmetic. So we're going to evaluate with the table. I'm going to pull 0 for my x because that will give me 3. E raised to the 0 power is 1. 1 times 3 is 3. If I put 1 in there, it will be 3 times e. So that will look like this, just to show you here for the first one. 3 times e to the first is just going to be 3 times e. So that's what you want to put into your calculator. You could either do 3 times the second button, or you could do just 3 times 2.718. And when you do that, you should roughly get 8. I think it's like 8.15. When I graph those in, I'm going to get those points. My asymptote is at the axis. Oop, I missed that one. Because I don't have a k value out here, right? It's not written, so we assume it to be 0, which means the x-axis will be what our line is approaching but not crossing. Our domain on this one, actually let me put this out here. Our domain on this is going to be all real numbers, right? All of the x's will be eventually part of this domain as it goes on and on towards positive and negative infinity. But our y's, that's what that asymptote is for, that the y's cannot be 0 or less than 0. So this right here states our domain and range. On 21, we have an a value of 3, so we're going to hopefully see some stretch. Our our R value is this -1 being multiplied by the x. So this is indicating that we should see a decay happening when we graph this. So hopefully that's what we see. I'm going to evaluate at 0 and 1 again. 3 e to the -0 is just 3e to the 0, which is going to be the same as the other problem, 3 times 1. And then now we have 3e raised to the -1st, which means we're going to flip the e into the denominator, just the e, not the 3. And then you're going to divide. 3 divided by 2.7128. When you do that, you should roughly get 1 again. All right, so plotting those on the graph here and here. And we see again that our k value out here is 0. There's nothing written there. In contrast, you can see on 22, we have a +3 out here. And on 23, we have a +1. So our asymptotes are going to change there to those numbers. But here again, we have the x-axis as our asymptote. So we're going to get closer and closer without crossing over. This lets us know, once again, that our domain is going to be all real numbers. And our range is going to be y greater than 0. On 22, our a value, so out here being multiplied by our exponential expression, is -1. So we can expect this to actually be inverted. Our r value is 1, which lets us know that r value corresponds to exponential growth, although because our a is less than 1, less than 0, we don't really refer to it as growth. So you'll see, I'm going to go ahead and erase that. But we do need to consider this asymptote here of +3. So I'm going to put that in just to guide us. It just lets us know where we need to stop our function. And then I'm going to plot in 0 and 1 again. All right, I'm not going to take the time to do that on the video, but make sure you're able to achieve these answers right here. And then if we plot those in, here and here, and then bring our line close to the x-axis, close to y equals 3. Here we can see that our domain, once again, is all real numbers. Our range is going to be whatever is underneath that y of 3. So y needs to be less than 3 for our range. And again, number 23, we have an asymptote at y equals 1. So I'm going to write that in before I forget to do that. I'm going to evaluate at x of 0 as well as x of 2. All right, I'm picking 2, you'll see in a minute here. I'm going to actually show you the evaluation on this. F of 0 is 2e, 0 minus 1. And that would give me 2e to, oh, then I can't forget the +1 there. Let me forget that. 2e to the -1st plus 1. So that's going to require me to, I'm going to leave the 2. The coefficient is not being raised to the -1st power, but the e is. So I'm going to put that down into the denominator, and then I'll need to add 1 to that. So when I say 2 divided by e and then add 1 to it, be careful with your calculator that you most likely are going to need to put this into parentheses in order to make sure it follows order of operation. You should end up here with a y of about 1.74. And then if we do the same thing, f of 2, this will be 2e to the 2 minus 1 power. So that's going to give us a 1 here. That's why I chose 2 for my x, because then that's going to give me 2e plus 1. And then when I put that in the calculator, I should end up with about 6.4. So plotting those points on the graph and then drawing in the line for the function, making sure that I approach y of 1 but don't cross it, should look very similar to what I've got right here. Now in 26 and 27, they're showing you two different formulas to use based on how your interest is accrued. So in both cases, your principal is the same. You're going to deposit this $2,200. Your interest rate is the same, this 3%. And remember, we're going to have to express that as a decimal, so 0.03. And then the time period for both is 15 years. Okay, so here's your T. Now, the difference is that in 26, your interest is compounding quarterly. So that means every year you're getting 4 periods where it's going to compound. This was the number that I think we talked about this in, I think it was 7.1. It corresponds to n. N is the number of periods that are in a year that your interest is going to compound. So 4 quarters in a year, that's how we get n of 4 on this particular problem. If it compounded monthly, then the n would be 12. If it compounded once a year, then your n would be 1. That's different than 27 because in 27, it's saying, let's suppose you put the same principal in of 2,200. You have the same rate of 3%, so 0.03 as a decimal, and then your time is the same, 15 years, but it's continuously compounding, meaning it's compounding daily. And so it's going to be a different formula. It's a natural base formula. It's going to use E. That's what the Euler's number, the E stands for the Euler's number, the natural base. And it's going to have a different formula. So we're going to figure out the difference between the two of them in this problem. So in 26, I'm just going to come out here and I'm going to plug in the numbers we know. 2,200 for principal. That 1 stays. That's part of the formula. We have a interest rate of 0.03 divided by our 4 quarters times our 4 quarters and the T of 15 years. All right, right here, I'm going to divide that 0.03 divided by 4 first, and then add it to my 1. When I do that, when I divide, I get 0.0075, add it to the 1, and I get this number right here. And of course, 4 times 15 is 60. So now I just need to use your calculators carefully here, but you're going to raise that number in parentheses to the 60th power first. And when you do that, you'll get 1.57. So you're just using your caret key here. This is nothing fancy. 1.0075, caret 60, enter. You should get 1.57. And then for a final answer of $3,444.50. All right, so let's see how that number changes. I'm going to come down here and plug it into this natural base function. Same principle. We're multiplying by E raised to the interest rate, 0.03, times the 15 years. So I'm going to figure out my exponent first. Multiply those two together, and I get 0.45. When I raise E, so now you want to use that second ln. It's going to pop up with E caret parentheses. You want to put in 0.05 and then hit your enter key. You should end up with 1.57. And now I made a smidge of a mistake here, which obviously I wish I hadn't done that. However, let me back up and show you what happened so you don't make this yourself. If you look here, I have 2,200 times 1.57. That's exactly what I had up here when I did the first formula. So I'm going to, if I multiply those together, I'm going to exactly what I got the first time, which is it's not precise. It's not precise at all. Because so here's what you need to do. When you raise these exponential expressions in this formula to the power. Don't round it. See, what I did is I rounded it, but if you don't round it, so like on this particular problem, I ended up with, dot, 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 1.56568, it kept going. Instead of rounding it, I just took that number right there and multiplied it by 2200. I didn't even clear it or anything, just hit your enter key and then do multiply by 2200. And it'll give you roughly this number right here that I got. If you do the same thing down here, so that means when I raised e to the 0.45, which is what I showed you over here, you're going to get an answer here. Instead of rounding that, I also rounded that to 1.57. But if I don't, I end up with a different decimal, and it's going to keep repeating. And so if I do the same thing, I hit enter here and just go ahead and multiply by 2200. Don't clear the calculator or anything out. Just let it take that unrounded number and multiply by 2200. Now I get $3,450.29. So you can see the difference there. It's roughly, what is that, $6 difference between the two figures.